Morning, good afternoon, and good evening. My name is Brian Foster. I'm a content director here at PingCAP, and I'll be your MC for today's event. In today's webinar, Brian Walters, Solution Engineering here at PingCAP, breaks down the major sharding challenges facing developers and architects. He'll then explore how one can avoid those challenges with a distributed SQL database. Brian has 20 plus years of experience as a database architect, engineer, and product manager. He's also spent 7 years at Teradata on their product engineering and product management teams, followed by 7 years with Oracle as a principal consultant. Now, before we get started, please feel free to drop your questions directly in the chat window. We'll be sure to answer them during the Q&A portion at the end of the talk. And with that, I'd like to hand it over to Brian. Brian, the floor is yours.
Awesome. Thank you, Brian. Hello, everybody. As Brian mentioned, my name is Brian Walters. We have an abundance of Brians on the webinar this morning. I'm happy to be here and happy to talk about this topic. It's a little bit of a, controversial topic about the idea of to shard or not shard. And we only have 30 minutes today, so I'm going to move through it pretty quickly. And we're going to try and have a little bit of fun with it because it's generally a bit of a serious topic. It's not something that is to be taken lightly, and it's certainly not something that we know that your general team that decides whether or not they're going to shard or not takes light. So we'll try and bring a little bit of levity to the discussion this morning and try and move through it as quickly as possible. To start with, we need to show our obligatory safe harbor statement. I'm just going to let it linger here on your screen for a moment or two so you can absorb it, get the whole thing in, and our legal team is happy. So with that, let's have a little bit of fun. Let's talk about a tale of an app, an application, or more importantly, a tale of a database. And I would like you to meet Bob. Bob is a developer, and Bob has been building an app. And he's been very happy with the progress that he's made on building his app. His app has a data access layer, or an ORM that it communicates directly with, and then it has a tidy little database that it uses for storing data. Now, to Bob's surprise and chagrin, Bob's app caught on, and soon Bob's app became a SaaS service, and his user base started to grow. So this means that Bob needed to make some changes. So some of the changes were in the architecture of the actual app, and then some of them were reaching out to hire some people to help him with it. So he converted the app to a microservices architecture. So it now had specific function-based services spread across the same data access layer, talking to the database. And he hired a team of devs to help him with the microservices section of it. He hired a team of ops to help him move it all to the cloud. And then he hired a team of DevOps to help him rapidly maintain and manage the entire infrastructure up in the database. And Bob's SaaS app had quite a bit of success. And as the SaaS grew, the data volumes grew. And soon the database was growing at a rate that caught them a little bit off guard. And they were a little unsuspecting of the data growth. And all of a sudden they started realizing, hey, maybe we should look at this because we're having a few performance issues. So they turned their attention to the database and they went through a series of attempts to scale the data, to handle the performance issues, to maintain reliability. The first thing that they did was that they just upgraded the size of the database, the size of the infrastructure in their cloud provider. And this worked until one day they were at the biggest size database that they could get inside of their cloud provider, and then they had nowhere to go from there. So they needed to change strategy. So next they split their reads and writes across a primary database and several replica copies of the data. This actually worked pretty well for them up until they got to the point to where their write traffic outpaced the ability of that single primary database to keep up, because this particular architecture did not scale on writes. So they got to the point eventually where they thought, what are we going to do? And it looked like the only choice that they would have was going to be to shard the database. Now with this, I'd like to step out of our story really quick and talk about our HTAP conference. Bob had gone to this HTAP conference and he had heard Henry Quinn, a software engineer from Square, present what his team went through when they were faced with the exact same situation. And one phrase in particular stood out to Bob when he heard Henry say that every single team that they saw at Square do manual sharding went from being a high velocity team to a low velocity team. Now, mind you, sharding was the official blessed architecture for scaling a relational database inside of Square. And Henry really desperately did not want to actually go there, did not want to shard the data. So you might be asking yourself the question, well, what's the big deal about sharding? Well, sharding seems like a simple enough solution to a complicated problem. You see, all you're really doing is taking a big database that tracks all of your data and breaking it into smaller databases that each track a small subset of your data. Of course, you have to add some logic into the app to tell the app which database to go to get to which specific piece of data that you want. But you might think, how hard could that be? Well, as it turns out, it can be pretty hard. And we'll talk about some of the reasons why. Most database platforms are equipped with a built-in native source replica model for data replication. Now, this model was originally designed first and foremost for disaster recovery, and that's important to understand. It was not designed as an efficient scaling technology. That you could open one of the replica databases and use that to offload query traffic from the primary database, that was an afterthought, not an original design characteristic of this source replica model. And even as an afterthought, this model, while it does provide read scalability, it does not scale writes, as there's still only one single database that can handle incoming write traffic. So for many teams, just like Bob's teams, their scaling needs simply outpaced the innovation in the database space. When they were focused on the limitations of their traditional databases and scaling needs of their application demanded action, they found themselves in a hammer and nail situation. The only tool that they had was this source replica model. And so they had to figure out a way how to scale the write load with this one single tool. And again, if you understand the hammer and nail situation, you understand that if the only tool in your bag is a hammer, then every problem looks like a nail. So with this being the only thing that they had, the only thing that they could do was make several copies of it and then attempt to stripe their data, spread their data across each of these multiple copies of this architecture. But this created a lot of challenges. There's no built-in support for sharding in these database platforms, so they had to build out complex orchestration layers themselves, or they had to reach out to third parties who specialized in these orchestration layers. And this was another layer of complexity on top of their database architecture. The application was built to talk to one database, so they had to code in complex shard access logic into the application itself so that it would know how to access the data that it needed to get from. And worse yet, every time they modified the shard topology, that shard logic in the actual application had to be updated. And this created an intense drag on the application team's ability to release new features and new versions of their product in a timely manner. And then if you want to talk about an ultimate inefficiency, if you just look at the example on your screen where we have 5 shards, in order to have these 5 shards, it equals running 15 unique database servers just to have 5 shards. Well, when Bob's team looked at what their world would look like after sharding, they were not pleased. They had their microservices. They also had a new and growing team internally that had reporting needs and needed to actually run some ad hoc SQL. They knew that at the data access layer, they were going to have to add this shard mapping logic. And then they also knew that all of these database servers underneath that they were going to stretch all of these shards across were going to have sharding orchestration built in to keep it all up and running and healthy. And that got them thinking about the real challenges of sharding, starting with complexity. Sharding tends to be a complex and time-consuming process. It requires careful planning, implementation, and ongoing maintenance to ensure that all of the shards remain balanced and evenly distributed. It offers very limited flexibility. Sharding limits the flexibility of the database itself, making it really difficult to do things like schema changes. And that in turn makes it difficult for the development teams to add new features to the databases. Very careful planning is needed before any database changes end up getting rolled out. And then there is the risk of increased latency. And this is because data is distributed across multiple shards, and there is no native way to join data across those shards, which means that all of that logic for joining data has to be provided by the application itself. And this also adds additional overhead and drag to the development team. Overall, the operational overhead is multiplied exponentially. Sharding involves multiple moving parts, which increase the time needed to manage the database, back up the database, monitor the shards, handle shard failures, and ensure data consistency across the shards. All of this adds up to just massively increased costs. Sharding is expensive, especially if it requires application developers to write significant code to handle the shard logic. The most important thing to remember here is that sharding is never a one and done thing. It requires constant upkeep, frequent redesign, and that results in ever increasing costs. So, Bob realized that it was time for a better solution, and he had some really core key points that they were looking for in the new solution. They needed one that was scalable by design, versatile by nature, and reliable by default, and preferably that was powered by open source. So Bob then found PingCAP and our product, TiDB. PingCAP is the company behind TiDB, which is the most advanced open source distributed SQL database on the market today. It is powering modern applications with elastic scaling, real-time analytics, and continuous data access. How, you might ask, is TiDB able to do that? Well, we'll drill into the architecture a little bit. At its top level, it really consists of two layers: an SQL layer, which we call our TiDB nodes, and then a storage layer. And the primary storage is called our TiKV nodes. It is MySQL wire compatible, so just about any MySQL tool can access a TiDB database with the default methods that you would use to access any other MySQL database. At the top level, from your application or your ORM, accessing the database looks just like accessing a MySQL or a MariaDB database. You can connect to any TiDB node. All of them are open for read and write, and they have some stateless characteristics to them in that if one of those database servers actually goes down, you can be reconnected to any other database server. So in this way, you have high availability provided baked into the product by design. The TiKV storage servers are independent storage nodes that also handle query processing themselves as part of the query plan process. They are a key value storage engine, and they are independently scalable themselves. Scaling is available just off of the top in two separate dimensions. If your concurrency goes up, you can simply add TiDB nodes for as many as you need. If your data volumes grow, then you can add TiKV nodes. This is great for seasonal workloads. This is great where scaling is needed for a temporary basis. Scaling becomes easy, predictable, and cost-effective. And this leads to a seamless user experience for your application user community. So a little bit of detail about how the storage itself works. TiDB breaks data into small stripes. We call them regions. The default size is 96 megabytes. And then it writes those regions across the TiKV nodes. Now, you might have 3 TiKV nodes. You might have 30 TiKV nodes. You might have 300 TiKV nodes. The first thing that it does is it writes one stripe across each node. And then it uses what's called the Raft consensus algorithm. Now, just a little bit of background about what Raft is. It was introduced in 2014, and it was designed to be a simple consistency algorithm for replicating through log shipping. Each region, each 96 megabyte stripe that gets written, gets 2 secondary backup copies written to 2 other nodes. So in this example that you're looking at here, region number 1 has a primary, which is stored on node 1, and then it has 2 secondaries, which are stored on nodes 2 and 3. Each of these is just a 96 megabyte stripe or a copy of the original 96 megabyte stripe. Raft and other basic log shipping, log replication mechanisms have been used openly in the market for a long time. Many of the non-distributed databases like MySQL, Maria, Postgres, Mongo, they all use a log shipping replication model. What sets the distributed databases aside, such as Spanner, Cockroach, Yugabyte, and TiDB, is that the non-distributed databases, they replicate the entire server, as we saw in that source replica model. We're not actually replicating the entire server per se, we're replicating the data in small 96 megabyte chunks. This creates an environment where you actually have data stretched across multiple servers in an access pattern that allows for the power of multiple servers to all come into play when servicing queries. Collectively, the set of three, the primary and the two secondaries, is known as a Raft group, and each of those individual regions is known as a Raft member. So what you're seeing here in our TiDB store is that region 1 is replicated across node 1, node 2, and node 4, whereas region 2 is replicated with the primary being on node 3 and two secondaries on nodes 2 and 4. In this model, you could actually lose a server and let's say that we lost node 3, the regions 2 on nodes 2 and 4 would hold an election, and one of them would become the new leader for that region. And the rest of the system wouldn't actually be involved in that type of a failover, but the failover would happen at the region level. This allows us to have really efficient separation of processing power at the SQL tier, processing power at the storage tier, availability in both layers, and scalability in both layers. And this is the point where I get to say, but wait, there's more. It gets better. We also have a columnar extension. Now, the columnar extension is used for aggregation queries. If you have a query that is just a single record lookup, that might get routed over to the row-based store on TiDB. We have this other type of node that is called a TiFlash node. These nodes store data in columnar format. And the replication from the row-based side to the columnar side actually all happens under the covers with no intervention needed from the user side, the administration side, the operations side. All you do is identify a table that you would like replicated over to the columnar side, and it simply adds a new Raft member over to that side. And so as those 96 megabyte chunks are getting inserted into the database, an additional replica is written over in the columnar format. Very, very, very efficient way of keeping a multi-mode database up to date with near real-time access to analytics. Very, very important. And we tied the entire thing together with a smart optimizer. And what you're seeing here is that the optimizer is part of the TiDB SQL layer. And we're demonstrating that in the explain plan that the optimizer builds, it automatically will route anything that has like aggregations in it, large vector style math, large summations over to the columnar side, and anything that is more transactional oriented or single record lookup will automatically get routed over to the row-based storage. So with that, I'd like to dig into a little bit of myth busting on the idea of distributed SQL. Bob started doing some of his research. We're going to go back to our story of Bob. And he started coming up with a lot of things that had been written and published about the idea of sharding. And the first thing that he saw was the idea that it's inevitable, that eventually everybody's going to have to shard. It's not possible to avoid sharding, that there is a scale point where you have to do it. Well, that's a myth. The reality is that distributed SQL provides better performance, better availability, lower complexity, and lower cost of ownership than manual sharding. It just does. The next myth was that it's necessary, that sharding is actually necessary to scale out write performance. Well, this is also a myth. The reality is that distributed SQL scales write and read performance as well as concurrency, query complexity, and data volume all in one product. And these are the areas that TiDB actually really shines. The other myth is that it's too complicated. Sharding is operationally necessary to manage large tables because managing those tables without it is too complicated. One of the online articles that I had read used the example of a 20 terabyte table, and it asked the question, have you ever tried to back up a 20 terabyte table, or have you ever tried to do some sort of change to that table, like adding a column? Well, the truth is that distributed SQL makes complex operations on large data sets very simple and efficient, and managing changes to tables that have massive amounts of data in them with online DDL is no different. It is simply a complex operation that the architecture is designed to make simple and efficient. The next one was that there's no other way. The only way to achieve suitable performance and scalability at the same time is to move away from a relational database model and move to something like a document model or a NoSQL model. This is also a myth. The reality is that performance and scalability are fundamentally implementation issues. They're not model issues. With the right implementation, you can have a scalable and performant and highly available SQL relational database with very, very, very little sacrifice. Speaking of sacrifice, the final myth is that it's just too expensive. Distributed solutions historically have been so expensive that they're out of reach for most companies. You know, the truth about this one is that distributed SQL solutions have been around since the early 1990s. Early implementations were tailored to large-scale data warehousing, and those solutions actually really were very expensive. The truth is, though, that a lot has changed since the early 1990s. And open source based distributed SQL offers cost competitive options that are well within reach of almost any company. Well, Bob then went out and looked at the landscape of the new modern database providers out there who had distributed SQL platforms. And what he found was that TiDB Cloud was the most comprehensive model of any of them out there, primarily having the ability to use both a columnar and a row-based store really helped out with multi-workload performance. And this was important to Bob because remember, he now had a set of users that wanted to do reporting against a real database. And he also had people who wanted to be writing ad hoc queries against that same database. What he found was that TiDB is scalable by design. It is an elastic distributed SQL database that helps to sustain his business growth, didn't require manual sharding. It provided click-through scalability. And because it was MySQL based, it offered a rich ecosystem of already existing tools that all just worked. To Bob's surprise and very, very, very happy discovery, TiDB Cloud, it was that database. It was the one that offered the easiest deployment, the best business continuity. It was the most scalable, and it offered real-time analytics all in one package. So what happened to Bob and what happened to his teams? Well, after implementing TiDB, they coded off into the sunset happily ever after, thanks to TiDB Cloud. And with that, I encourage everybody to go out and try TiDB Cloud today and become a high-performance team, just like Bob and his teams. And we have a few minutes left where we can pause for questions now.
All right, excellent. Great presentation, Brian. Really informative and nice kind of walking through kind of the different challenges and different things that, again, are out there with sharding and kind of moving to distributed SQL. It does look like we have a few questions, so I want to get to those so we have some time. So, can you please, one of the questions we have is, can you please explain the benefits of being an open source SQL database?
Yeah, well, it's no different than any other open source product out there. And that is, you have the benefit of having developers around the world contributing to the product. You have the benefit of lots of people contributing to fixing bugs. You have the added benefit that anybody who wants to actually look at the product, look at the code base, has the ability to do so. Our product is actually, and most of the products in this space, both Cockroach, Yugabyte, and TiDB, they're all open source. So what this does is it helps to speed the innovation of the entire industry. of distributed SQL, all to the benefit of the database consumer.
Gotcha. No, that's good. That's a good answer. Looks like, yeah, we have a bunch more here. Let me try to get through these. So how does TiDB eliminate data silos? And can you provide an example?
Yeah. So several years ago, the term polyglot became very in vogue. And what this was a way of describing a best of breed approach of storing data. So if you had data that needed rapid ingest, then perhaps the fastest way to do it was to have a NoSQL database or maybe a columnar store database. And if you need a transactional consistency, then you use something like MySQL or Postgres for transactional consistency. And if you needed something for time series, then you use a time series database. And what this ended up resulting in is that you had applications that might be connecting to 3, 4, 5, 6 different databases. Well, it turns out over a period of time that as all of those databases grow, it ends up being incredibly complex. And the number of skill sets that you have to maintain in order to have all of those databases up and running and current and backed up and highly available is a tremendous amount of overhead. And in addition to that, all of those individual databases were siloed. And most of those databases didn't have easy to access APIs for anybody who was not part of the developer community. So a lot of people who were on the back end of the house were cut off to access to that data. So not only was the data siloed, but the data was cut off from a good portion of the user base. TiDB Cloud actually helps to eliminate that problem because some of the core reasons for having these best of breed solutions out there are automatically covered as basic core capabilities of distributed SQL databases.
Gotcha. No, that makes a lot of sense. Another one here. Do we need to redesign our application if we move away from sharding?
One of the benefits of using a product like TiDB is that we actually have the tooling built into it to do the migration itself. So we can de-shard a database with our TiDB tooling. The application itself would need to have some redesign if it's got all the sharding logic built into the application. The good news is that the redesign is a simplification of the application architecture. You're actually removing the shard logic, you're simplifying your code base, and you're actually, from the perspective of the application, only connecting to a single database connection endpoint.
Gotcha. No, that makes a lot of sense.
Mm-hmm.
Here's an interesting question. Is the resiliency characteristic of a distributed SQL database configurable? For example, if I want it to be resilient to multiple node failures or resilient to correlated node failures in a given availability zone?
Yes, it is. I've been using the example of 3 copies. That is totally configurable. You can have more copies if you want. And then what TiDB Cloud does is the minimum is 3. And so when you deploy into a region, one of those storage servers is spread across each AZ. So by default, you have a storage server in one of 3 AZs.
Gotcha. No, that's a good answer. That makes sense. Looks like we're almost, but it looks like we have time for one more. So how can, one question that came in, and I think this is a pretty simple one, how can folks migrate from MySQL to TiDB? What's the best ways to get started?
So the best way to get started is to go out to tidbcloud.com and fire up a TiDB server and just take a look at it and start playing with it. If you get to the point to where you want to try a migration, I encourage you to reach out to us so that we can actually help you with it. One of the easiest things to do is just do a MySQL dump, and then you can import that into TiDB. If you happen to be on one of the other cloud providers and you can get Benlog replication working on those providers, you can get Benlog out. We can ingest that Benlog. We have a lot of tooling that is designed specifically for this type of migration. And depending upon what your scenario is, we can point you to the right tooling set.
Excellent. No, very good answer. Well, it looks like we are at time. So again, I want to thank everyone today for attending today's talk. It was a really great, informative discussion. We'll be sure to make a recording available to everyone who registered for the event in the coming days, and we'll be sending that out via email. And as Brian mentioned, again, if you'd like to give TiDB a spin, you can spin up a free trial of TiDB Cloud. And again, you can do that by heading to tidbcloud.com/free trial. So again, thank you all, and I hope you all have a wonderful day.
Bye, everyone.
Take care.